Imagine you are in a train traveling at 80% the speed of light.
Let us suppose that the train has a headlight located in its front end. From your point of view, the light coming from the front of the train travels exactly at the speed of light. Now let's say your friend is an observer from a certain distance from the train.
Here comes the interesting part. It would make an intuitive sense to think that from your friend's perspective, she would observe that the light coming from the headlight travels at 1.8 times the speed of light.
Because it would have its own speed plus the speed of the train. Unfortunately, this is not right.
In reality, your friend would be observing that the light coming from the train travels exactly at the speed of light, at about 300 million meters per second. This strange phenomenon can be explained by special relativity. The special theory of relativity tells us that the laws of physics are the same in all non-accelerating observers, and the speed of light within a vacuum is the same no matter the speed at which an observer travels. It simply tells us that time and space are relative, and they are inextricably connected. Now, let us prove this theory with a simple equation.
You might probably know that the distance is equal to the product of speed and time. This tells us that if the distance is increased and the speed of light is constant, the time would also increase. Now let's go back to the train problem. Let's say you flashes a light on a mirror inside a moving train. From your perspective, the light travels from the flashlight to the mirror and back to the flashlight. But from your friend's perspective outside the train, she sees the light travels diagonally as the train travels. From her point of view, she will observe that the light you flashes travels a much longer distance than you have observed.
You and your friend experience the same kind of event, but you perceive it in a much slower time than she does. Therefore, from her perspective, your time slows down, and from your perspective, her time speeds up. This phenomenon is called time dilation, which is represented in this equation.
Where t prime is the time measured by the stationary observer, t is the time measured by the moving observer, v is the velocity, and c is the speed of light. Now let's try this with our train example. Let's plug in the speed of the train and the speed of light. Then simplifying the equation would tell us that your stationary friend would experience 5/3 times the time you experience. That means her time is much longer than yours by 67%. Thus, the faster you move through space, the slower you move through time.
Special relativity taught us that doing nothing speeds up our time. So start moving, then keep the motion going. Remember that time is relative, but moments can never be retrieved.